Okay, so this example is actually pretty similar to the last example where we looked at extracting historic mining extents from topographic maps. And that our goal here is basically a binary classification, so presence, absence, 0, 1, and we're using 3-band data, and we're relying on semantic segmentation methods. The main difference here is we're going to look at a different data set and a different type of classification problem. Okay, so what we're going to work with specifically in this example is the Inria aerial image labeling data set, which is a pretty good common benchmark data set for semantic segmentation and binary classification tasks. Specifically, this is looking at mapping or differentiating buildings from not buildings. So again, it's binary classification problem. This is an interesting data set for a couple reasons. First, it's really well put together. It's really easy to use. And it also represents building footprints across a wide variety of landscapes. So there's been data, the data were produced for different locations in the U.S., such as the city of Austin, Texas, and Chicago, Illinois. And there's also data available for portions of Austria. So, for example, the area around Vienna and the area and around Innsbruck in the mountainous Tyrol part of Austria. So it's an interesting data set to train and test and validate on different data sets, look at transferability and model generalization. Okay, and then this data set specifically relates to, or specifically was introduced in this paper. So after Maguri and L here and others, so they have an experiment where they looked at how well their models trained in certain areas, extrapolated to new geographic extents or new areas where the building presentation might be a little different. So we're going to kind of replicate part of this paper, but we're not going to do it in the level of detail that they did or the number of different experiments that they undertook. Okay, so to obtain this data, you can download it from this website. So you have to provide some information there, and then you can download a series of compressed folders that all have to be uncompressed collectively. Once that's done, you're going to end up with a data, or let me pull this over here. You're going to end up with a folder that looks like this. So new to aerial image data set. I might change if there's any updates to the site. And then inside of here, you're going to have a set of test data and a set of training data. In this example, I really just use the train data, but it does provide both. Note with the test data, it only gives you the images. It doesn't give you the masks. And then for the training data, you get both the images and the masks. So here's the images folder are the images there. And the GT folder here are the masks where 0 is not building and 255 is building. And then within the images and masks specifically, each image tile is includes the city name. So these are all the Austin, Texas tiles, Tyrol, Austria, Vienna, so on and so forth. Okay, so what I'm going to do as an example is I'm going to try to create a model using the data from Austin, create a separate model using the data from Vienna, and then we'll test how well both of those models perform by extrapolating out to the data collected over Tyrol. And my hypothesis here is basically that the buildings in Vienna are going to be much more similar to the buildings in Tyrol, since they're both in Austria, as opposed to Austria, the Tyrol versus the data from Austin. So my thought is that we'll have a better model fit from the Vienna data than we will from the Austin data extrapolated to Tyrol, Austria, near Innsbruck. Okay, so some of this is going to look familiar. Again, the goal here is just to kind of reiterate the process of doing deep learning using this open source software stack that we've decided to use here. So I'm basically using a lot of R scripts, but doing the the deep learning training and inference using Python. Okay, so first off, we want to make sure we have a Python library available. Let me just, or a Python environment available with all of the required libraries and GPU access and everything. And again, we set that up in a prior video. So in order to use that, you have to call the reticulate package. So you can run your R code here in RStudio. And then we want to specify our specific environment that was set up for this task. So this is my PyTorch SB environment, and then let's test and make sure it got configured correctly. Okay, so you see here we have our environment there, and it also tells us NumPy, the NumPy version, so it looks like we're set up. Okay, so we should be set up to use Python. The next step is to go through and do some data prep. Okay, so we're going to move over to this folder here, which I use to generate some image chips. Okay, so first thing I do is list all the images that are in the training folder, and specifically the images subfolder, and I do the same thing for the GT folder, which is the masks. So let's just run those and see what we get back. Oops, forgot to grab the in parenthesis there. Okay, so this should create two objects, images, and as you can see there, this is a character vector with 180 records in it, because there's 180 images in there, and then we have the mask vector there, which is effectively the same, so 180 of images. Okay, and then I merge those into a data frame, so I have both the image and mask data in one location. And I want to be able to stratify my selection of tiles or images by city. So I used some functions here from Stringer to do some manipulation of the characters. So first thing I do is I get rid of any, I believe it's spaces, any periods, and replace that with spaces, so we don't have any issues with that. And then I pull out the city name and remove the file extension, and we add that into this city column in our data frame. So at this point, what we end up with is this object. So we have the name of the image, the name of the mask, and as you can see here, they're the same. That's how they're related. And using that string manipulation, I just pulled out the city name from the path there. So that gives us like kind of a unique field of city or the city name that we can use to kind of stratify any of our selections. And then just to see what we have here, I use dplyr to group by the city field and then count, so we have see the number of tiles we have for each city. And as you can see down here, there are 34 tiles available for each city. Okay, and then I also want to have the full folder path, so I create two new columns in the data frame. This image full column, which should just take the full file path on my local machine, and then add the file name there, and then just the same thing for the mask path and the file name. So we've run that. Okay, and then if we look at this object again, now again we have our image name, mask name, city, and then the full file path and the full mask path. All right, and then I'd like to break this data set up by city. So I'm just using dplyr here to do some filtering. So I filter out all the Austin, Chicago, Kitsap, Tyrol, and Vienna tiles into separate data frames. At the end of this, we're going to use we're going to predict out to all the images in Tyrol. So I'm writing that out as a CSV file here. So I'll just show you that in my folder. So if I go to this Inria folder, this is the result there. So this is Tyrol images, and again we get this CSV file with the image name, the mask name, the city. These are all the Tyrol ones again, and then the full image and mask path. Okay, so the next thing we need to do then now is actually take these larger tiles and break them up into image chips. And if you remember from our last example, we had a function that we created in R to do that. So let's open up that file just to take a quick look at it. Again, I'm not going to go through this in detail, this time since we already did that with the prior example, but just to highlight what's going on here. So I'm going to go into, I just made a copy of that into my Inria folder here. And again, I made this chipit function that goes through and makes image chips from tiles. So this function is already called in. Actually, is it not? Oh, it's not called in. But we're not actually going to run it anyway because it takes a long time. But basically, you just run this to call it in as a function. And again, this is R, not Python. And then once we have that function called in, I just go through and make image chips for each city, and I do that in separate folders. So as I create this chips2 folder with an Austin subfolder, Chicago subfolder, Kitsap, Tyrol, and Vienna. So those are all the city data sets. Whenever I ran this, Chicago flagged an error, and I wasn't really sure why. I ended up just not using it for the rest of the experiment. But you should note that you may have the same issue. Mainly, I'm just relying on Austin, Tyrol, and Vienna in the example, so I really didn't need to make the Chicago or Kitsap examples, but I did here. Okay, so again, what we're doing here is using our function. We're doing it in a for loop, so it goes through each of the tiles in each of the city data sets. Again, there's 36 in each one, and it goes through and makes the tiles. So it's required that we give it the image path, the mask path, the number of channels, the size of the chips. So this is going to produce 256 by 256. The stride, I set the stride X and Y the same as the size, so there won't be any overlap. If you wanted more chips or some overlap, you could change that. Output directory, and we're using all mode, which basically means it's going to dump all the positive and background, so all the chips that had buildings in it and chips that didn't have buildings in it, into the same folder. There's not a real big issue in this data set with data imbalance, so we're not doing like what we did last time where we put the background and positive samples into separate folders. We're just writing them all into the same place. So I just do that for each of the data sets, writing to a different folder to get out the image chips. And again, I'm running that here because it takes a long time, but just to show you what that creates is here's that folder. Again, we have a different folder for each city. Let's look in Austin here. So we have our images, and there's all of our 256 by 256 image chips. Excuse me. And then there's the associated masks. And that's the same for each city. All right, so then I want to make a list of all these chips so that I can use that in my Python code. So that's what I'm doing here. So effectively, I'm just listing all the files in the image directory and the mask directory, and I'm using the PNG extension here because that's what they were written out to, and I'm going to get back the full name. So I just do that for each city. So if we run this, this takes us a little bit longer than before because we have a lot more features now because we're not dealing with the tiles, we're dealing with the chips. And then we can merge those into data frames. And let's just look at one. So we'll look at this Austin chips data frame here. So you can see that in the data frame we have the path to the image and the path to the mask, and there's a total of 14,400 samples. Yep. And then we just write those out to disk, so we have them. And then again, we'll just look at that here. I wrote them out in this chips folder. So if we open one of these, it would have all of those image path and image mask, or image and mask paths. So that's how we're basically creating a list of all of our training samples that we're going to use in Python. Okay, so that's basically all the prep work. So we've split up by city, and we've created image chips for each individual city separately and placed that data into separate folders. So now we're ready to move on and start to actually train our algorithm. Okay, so now we're going to switch over to Python. All right, so again, this will look fairly similar to what we did with the topo map mine extraction example, but there will be some differences. So I'm not going to, again, go through this in a lot of detail, but I do want to point out some key things. All right, so we're pulling in our libraries here, again, working in Python. So now we're in Python code as opposed to R code. So we're pulling in NumPy, Pandas, Matplotlib, OS, CV2, Torch utilities, dataset, and albumentations, Segmentation Models, PyTorch, and then we're calling in this train test split function from scikit-learn. So let's run that. And again, as long as your Python environment set up correctly, and you've read it in correctly with Reticulate, you should be good to. It should load in all those environments. If something's not working, then something's up with your environment generally. Okay, and then I just changed the working directory here to my folder that has this Inria data in it. And then we're starting to work with actually building our model. So the first thing we're going to do is set up some parameters. So we're going to use the ResNet 18 backbone as the encoder. This is smaller than some of the others. That's why I'm using here as an example. If you do play around with these, feel free to change this. There's ResNet 32, 101, 151, or 150. I can't remember. But then there's other backbones. So you can play around with the backbones and see if it would improve it. We're going to start off with ImageNet weights as opposed to starting off from randomly initialized weights. These are RGB images, so it seems like starting off from ImageNet would make more sense than starting off from scratch. Since this is a binary classification problem, we're just specifying the one class they are building, and we're using a sigmoid activation function as opposed to something like a softmax, because again, this is binary. And we want to work from our GPU, so we're setting our device there to CUDA. So those are just setting some variables. Again, there I'm just testing to make sure that it's seeing my GPU and I have access to it. If you try to run this process outside of the GPU, it's going to take forever. So you definitely want to make sure you have GPU resources available. So here you can see I have one GPU available. It's my GeForce RTX 2080 Ti. Alright, so that looks good. And now I'm reading in those data frames that we created in R that lists out all the chips. So I'm just using Austin, Vienna, and Tyrol here. So let's run that. All right, and then since we didn't have separate training, test, and vouch partitions for each city, what I'm going to do is create training and testing partitions using this train test split function from the scikit-learn library in Python. Validation, we're just going to rely on the Tyrol data, so we don't need to worry about a third split. So we just have our basically training and testing. So basically this is using like a 2-for-1 packing. So we have basically this creates a couple different objects. So we're unpacking it into this Austin train and Austin test data set. And the same thing with Vienna. I'm setting the test size here to 0.3. So what that means is roughly 30% of the chips are going to be withheld for testing. So let's run that. Okay. All right, so now we're ready to specify our data loader. So again, we're just subclassing the Torch dataset class, and so that it loads our data correctly. This one's actually pretty. It's in many ways simpler. Let me just expand this a bit. It's a little bit simpler than what we did with the topo map because we're not doing any like random selection or anything within the data the dataset generator. So again, we have to have an init. We have to have an init function, or I guess method, the get item method, and then the length method. So those are required. So here we're effectively just feeding it a data frame. You can feed it a list of classes and then some transforms. So we have self.dataframe is data frame, self.transform is transform. So what that should do is call the data frame that lists out all of the files. And then again, the get item method, what that does is this basically it's a template for how to generate a specific image mask chip pair. Right, so again, it's going to from the data frame. It's going to use the index 1 column, which is the second column, right? Because it's indexing at 0. So this is column 2 and column 3, which holds the image path and the mask path. So that's just reading in the path. Then we read in the image. We swap the band order, so BGR to RGB. Then we read in the mask unchanged. I define them both as unsigned 8-bit, and then we expand the mask dims to out 1, and that's because it's grayscale, so it reads it in as width, height, and no channel band, so effectively I'm just adding in a channel band there. And then this goes through and applies transforms if we wanted it to apply transforms. If it doesn't, then we do what's in the else statement. So once those transforms have been applied, then we can convert this into a torch tensor as opposed to a NumPy array, which is what it is up to this point. So we'll do torch.from NumPy to convert to torch for the image. Same thing for the mask. Remember, with torch, the band order is different, so we want to do channel height width as opposed to height width channel. So I use this permute method to change the dimension order there for the image. And then we want it to be scaled not from 0 to 255, but from 0 to 1. So we just simply convert it into a float and divide by 255 to rescale. And then for the mask, we do the same thing, change the band order, divide by 255 to get a scale from 0 to 1. Again, the mask in this case was set up as 0 to 2. 0 is background, and then 1 and 255 is building. So if it was set up as 0 is background and 1 is building, then you wouldn't have to divide by 255. And this is the same process, just without the transform applied. And then lastly, the length method would give back the length of the object. Okay, so let's run that data loader to initiate it. Click enter here. So now that should exist, so we can apply it. Then I set up the transforms. Again, this is using albumentations. I effectively just used the same transforms I had for the topo map example. But again, you could feel free to go through and play with this a bit, change some of the settings, add additional transforms or remove them or augmentations. So again, I'm really just applying random brightness, contrast shifts or changes, random horizontal vertical flips, applying a blur, and again the P there has to do with how often that's applied. Again, these 256 resizing is probably not necessary because all the ships should be 256 by 256 natively, but we're just doing that for good measure. So anyway, that just defines our transforms there with albumentations, and then we initiate our data sets. So here I'm reading in my Austin training set from the Austin train object there was created using that scikit-learn data split method, and the same thing for test. Then the difference here is we're setting the train transforms for the train and the test transforms for test. And then as a test here, we're just going to split look at the length. So we have for training 10,080 samples, and for validation 4,320 samples. Remember, there was 14,400 chips, so that adds to that, so that makes sense, right? Okay, so that looks good. Again, we're going to look at the shape just to make sure that makes sense. So if we're to do that, we have to specify the data loader. So here we're doing a batch size of 10. That's the main thing. Setting number of workers to 0 since I'm on a Windows machine. And we're just grabbing our different data sets there. Note that if you're working on a different machine, you may have to change the batch size. If you run out of memory, if you have maybe a better graphics card or more memory than I have, you can maybe set it up higher. But 10 seemed to work well for me for this data set. Okay, and then once we have the data loader there, we're just going to pull a batch and look at the shape, make sure it makes sense. Okay, so this spits out a batch of images with dimensions 10, 3, 256, 256. So 10 is the batch size, so 10 images for batch, so that makes sense. 3 channels, height, width. And then the mask is the same thing, except it's 1 for the channels as opposed to 3. And then we can see they're both defined as 32-bit here. For the mask, it could be defined as long, so it would be like 64 int 64, but didn't seem to matter in this case. So I just left it at 32 float. And here I'm pulling one image out from the batch and then spitting and then writing some information about it. So again, now we lose our batch dimension, so it's just channel, height, width. That's the image, channel, height, width, mask. Both 32-bit float tensors, and they're both scaled from 0 to 1, which is what we expected. Okay, and then if we want to see them, we're just doing a plot here. Let's see if this runs. Oh, that makes the object. Let me put in a plot.show here. Get it to plot. Let's run this again. Okay, so there's an example image. This is a fairly large building roof there, and then this should be the associated mask. Oops, I always do that. There we go. And so those look like they line up well, so it looks like everything's getting read in correctly. Okay, so we have our data ready, so our data set, our data loader. So now we're going to initiate the model. In this example, instead of using UNet just to use a different algorithm, I'm applying DeepLabv3 which is built into the Segmentation Models library. And then I'm feeding it the encoder, which in this case is the ResNet 18, the encoder weights, which is getting from ImageNet. The classes is the basically just building, and then whatever activation function. So this is binary, so we're using a sigmoid activation. So that will initiate the model. Okay, and then for loss, we're using a combination of dice loss and BCE loss, right? So binary cross entropy loss and dice loss, and they're equally weighted. If you wanted, you could add a weight to these to change the relative weights. So we're using a combined dice and BCE loss in this example. And then we're going to also calculate F-score, accuracy, recall, and precision. So this is, again, the same as the topo example. And we're going to use the atom optimizer. And again, I'm not setting a learning rate here. We're just using the default. Again, that's something you could experiment with to maybe improve it. And then using the segmentation models library, we define our training epoch and our validation epoch. So the model, the loss function, the metrics, the optimizer, the device, which will be our GPU, and then verbose means it's going to print some progress as it goes. And then after that, we're ready to run our actual training loop. So here I'm just running it for 10 epochs. I probably needed to do it longer. Again, this is just an example. I didn't want to take forever. So you probably want to play around with this, let it run longer than 10 epochs, but that's what I just did here as an example. Okay, and then I'm having it save out the model, the best model based on the F-score as best_model Austin, because we're going to train on the Austin data first. Again, I'm not running that here because it takes 3 or 4 hours, depends on your machine. Could take longer. It would take a lot longer if you had more epochs. So anyway, we're not going to actually run that. Okay, so let's call in now our Vienna data and make a model for that. And this we don't need to go through because it's the same process. So this will give us our Austin model. All we really... Okay, yeah, so anyway, this is basically the same process. I'm just swapping out Austin with Vienna. So again, we create our Vienna data there, our data loader, test, make sure everything looks all right, initiate the model, set all the model parameters, and then go through and iterate over epochs. Yeah, and again, we're just saving it out to best model Vienna here as opposed to best model Austin, so we don't overwrite our original model. Okay, and then lastly, just to validate the model, first I load one. So here, let's see what we want to do here. This is, let's look at this Austin one first. So here I'm just loading in. I'm going to load in some validation data. This is the Tyrol data. And then I'm going to read in the model. So this was the best model that I got post-training. Define an evaluation epoch, and then this would print the logs. So if we run this, it should print out some results. So let's run that real quick, see what happens. This might take a little bit of time, but as you see here, it's iterating through the examples and from Tyrol, and it's spitting back the loss, the F-score, the overall accuracy, the recall, and the precision. And then here we're just doing the same thing, but with the Vienna data. So as that run, I'm going to run both because it takes a really long time. But the key thing here that I found was that our hypothesis was effectively correct. So we found that the Vienna data did yield a better performance in terms of F-score and recall precision. As opposed to the Austin data, or the model trained on the Austin data, which makes sense that again the Vienna data would probably be more similar to Tyrol, Innsbruck, Austria than Austin, Texas would be. So that generally confirmed our hypothesis. So anyway, that's just running that val process. The last set of code here is again really similar to the topo map example. We're running we're setting up a function to visualize the output, and then we're visualizing the image, the ground truth mask, and then the predicted mask. All right, so while this is finishing up, I'm just going to step forward to the other the other components. So once we have a model, we can use it for inference. So I have this infer Python function Python file here. Again, this is similar to the topo map one. So effectively, we can define a model here. We're just redefining our model. And then I create this geoinfer function that goes through, pulls chips out from a tile, and infers onto the chips. And then, it's doing some things to like try to remove edge boundaries and stuff where the predictions might be worse. And then it writes the result out to a TIFF file with the same spatial reference information as the original image. In order to run this on multiple images, I just set up a loop here. There it loops through, in this case, all the Tyrol images, makes a prediction for each one, and throws it back to a folder. Okay, so let me show you where that ended up. So if we go into Inria here, predictions, these are all my Tyrol predictions. They don't show anything because it's really just like a 0-1, and that's not showing up in the stretch. Let's just open one of these up in QGIS while this is running and just have a look. Okay, so let's, well, this is going to be a weird projection. I'm just going to reopen this. Let's do discard here. Just going to reopen QGIS. I'm not making a project or anything because I'm just using it to visualize some of the data. Alright, so let's go into that folder and grab a couple examples. Alright, so this is the Inria dataset, training. Let's just grab the first Tyrol image. So that is the mask. And then the image, again, we want to just pull in the first one. So there's the associated image, and then we want to grab our prediction for that specific tile. And that should be under predictions, and we want this first one. Okay, so let's zoom in here and just have a look at the output. So again, I didn't train this long enough. There definitely was, and this isn't an amazing model. Again, this is just to visualize the result. So anyway, this is what we predicted. This is the original. So you can see they do line up somewhat, but they're not perfect. A lot of the buildings aren't nice and rounded off, and some things are missing. So again, this needs some additional work, but again, this is just trying to show you an example of how to go through this process. Again, we want to try to do an assessment not just visually, but in some type of quantitative way. So that's what we'll look at in our last set of code here. Okay, so let's close this down. It looks like this is about done. Okay, so for this, for the validation set, using the image chips, you see the accuracy was fairly high, but that's mainly because there's a lot of not building. Precision was 75-ish, recall was 60-ish, so it looks like it's having some more issues with recall than it is with precision. So how could we potentially fix that? Well, obviously we could train it for more epochs, we could play around with data augmentations, we could unfreeze parts of the model and let it update weights. You could also maybe run it with a different loss function that maybe weights recall higher than precision. So there's some options there. Again, it's just a lot of playing around with the data, the architecture, the hyperparameters, and whatnot. So again, whenever you're doing this type of validation, it's just basically doing it on a chip-by-chip basis. So I think in a geographic sense, it makes more sense to do your validation on the entire final merged product. So that's what this last set of code does. And again, this is similar to what we looked at with the topo example. Okay, so I'm creating a function here called eval classification that accepts reference and predicted data and spits back some predictions. And then specifically, what we're going to look at is getting back the accuracy, the kappa statistic, the F1 score, precision, recall, specificity, negative predictive value, and then merge all that into a final thing. And since we have multiple chips here, then we actually are going to do that in a loop. So I just set up a loop. It goes through each of the tyrol chips, makes these calculations, and writes that into a data frame. So what we end up with is something like this. So we have the original file name, the predicted accuracy, the kappa statistic, the F1 score, the precision, the recall, specificity, negative predictive value. And we have those for all of the images that we looked at. This is a total of 36 images. So similar pattern, precision is generally higher than recall. Specificity and NPV are pretty high, which explains why accuracy is high when F1 score isn't. So in short, there's room for improvement here. But this was just a quick example, so we didn't do a lot of fine-tuning. All right, so that is this example. So this is another binary classification problem, but now using some aerial images and looking at building extraction as opposed to using historic topographic maps, but still working in the same environment where we're making use of PyTorch and Python and R.